Okay, so welcome everyone. I tried to talk about the PhenoRob related activities that happens in our lab and try to present it for the people from the other research units. So I'll try to approach this from the functions point of view. So what can we provide as functionalities that may be relevant for you for doing your research? Before I start with this, a few words what we are doing. So we are strongly related to link perception and action through mobile robots. That means we have mobile devices which can drive through the environment or can fly through the environment, perceive the environment with their sensors, and then turn this information into some kind of model so that we can derive appropriate actions from this. This can start with, for example, building robots exploring the catacombs under Rome and Naples, building 3D reconstructions of sites you cannot enter anymore today. Since a couple of years, or actually since I started in Bonn, so 2014, working also on robotic systems in agriculture, mainly in a collaborative project with ETH Zurich, Freiburg, Rome, and a few other places. The research unit Mapping on Demand, founded by the GFG, which has been started by Wolfgang Fürstner, my predecessor, and which I took over in phase 2, deals with flying vehicles, visual perception, but also other forms of perception like georeferencing, IMU data, laser-based laser information in order to build 3D models on the fly. And I've been working on navigation aspects in urban environments and autonomous driving applications. And what I want to talk today is actually a few parts. The first thing is more on the applications that we have done in the context of agriculture, especially crop farming. And then the last 4 parts are more from the technical perspective, but not diving really deeply into the techniques, but showing what you can do with the technologies which we are using. So the first thing is more application driven, and the other parts are more techniques driven, but still on a high level, always trying to answer questions, what can we actually do with this? So start with the robotics applications related to agriculture, and here we have been concerned with the perception problem for quite a bit. So the first question we now can answer, which pixels of an image belong to crop, wheat, or any other class? So this is one question that you have if you bring autonomous systems to the field. You take a camera, record the scene, and you want to say, what do I actually see? So the green thing that I see, is it a plant that I want to have on my field or a plant that I actually want to get rid of? And so this semantic interpretation or semantic segmentation that we're executing, for example, takes an image, an input image like this one, and labels this, and everything which is kind of dark green here is the value crop I'm interested in, and the small red dots over here are, for example, small weeds. So actually, based on RGB or RGBD plus near-infrared, so 3 or 4 channel cameras, actually providing in real time a high quality semantic segmentation. We can do this based on ground vehicles, so there's one of the platforms what you actually can look in here. You have a very small field of view, and then we actually able to label every pixel and say what is a plant would like to have, what we don't want to have, or what is background information here shown in blue. This is always, you see always kind of this CP14 over here. This is, I think, approaches linking to one of the core projects proposed in PhenoRob. So CP1, core project 1 on 3D crop reconstruct or 4D crop reconstruction, and core project 4 on real-time intervention in the field. Just to kind of create the links where I think these techniques are important. We cannot only do this with ground vehicles, we also can do this with flying vehicles. And one of the efforts that we have done is taking perception from a standard out-of-the-box Phantom 4, so one of those drones you typically use for creating YouTube videos. It became very popular for that, with a standard camera, and not requiring special hardware to do that, so that we can fly with off-the-shelf components which are comparably cheap, and turn them into maps where we can spot weeds, or in this case sugar beets. And some of the efforts that we have done in here is trying to speed up learning and to improve the technologies from the point of view that we need less training data to train those classification systems. And so one of the things we have done is that we said, okay, there are nice deep learning techniques which are out there which we can use, but we have been building those classification systems for a long time, and before that we had actually users, experts, designing features which are good to solve the problem. Today the deep learning based approaches are typically better in generating those features, but they need a huge amount of training data, and this huge amount of training data we typically don't have. So we tried to say, let's start with what kind of the users or the expert have designed in terms of features and put this as extra representation in those networks, and then let the system learn features based on this input information. So if you start with an identity mapping in the beginning, you already start with what the users designed, but the system can actually adapt those features and then improve them over time. And this has led to a big improvement that we can reduce the number of training samples that we needed substantially, let's say a factor of 10 for providing the same results, just by providing what user thought is good in the beginning and then lets our system adapt that over time with very little cost that we need to add to that. So in this way we can kind of integrate some kind of background knowledge into those systems. First, we can learn much faster, but the key gain from this technology is also that it translates better to other environments. So if we train our classifiers here in Bonn, for example, and apply them to fields in Zurich, the standard classification system actually has a hard time for doing a good job. But if you already provide features which you think are good for doing this, you typically can translate to new fields much better because the system is kind of less overfitted to the local conditions we may have in Bonn. And this was kind of one of the things that helped us a lot in actually building those systems which can generalize much better to new environments, new fields by providing this extra information. Something that we haven't exploited a lot was spatial arrangements. So in the beginning we worked mainly based on appearance. And so if the system drives over the field and we actually record data here, and especially if we have plants which are planted or crops which are planted in rows, then we should actually exploit this information. So one image, this is always kind of the input image that you get, and this is kind of the classification result. If you have one, it's more tricky to separate or to identify what your crop is or what weeds are. But if you take a sequence of them, spatially arranged, you can actually see that you have your crop row over here. And the question is, how can we actually add this geometric information spanning over multiple images into those learning-based approaches? And here we used combinations of temporal encoder systems. So you have an encoder, a visual encoder system and a decoder system. This is a classic classification system that you have. But you can also take this spatial information into account. And this helps you to learn spatial patterns that do not need to be provided by the user, but the system learns it on its own while driving over the field. That, for example, the probability that crops appear in certain patterns are more likely for crops, but for example not for weeds. And the system can learn that over time quite quickly, which again helps you to generalize to new field conditions or field environments. So if this is data A where you trained your system and then you go to a different field where the image conditions are kind of different, the growth stages are different, it still helps you to provide high quality generalization, which from our point of view is one of the key bottlenecks. So we are all able with standard out-of-the-box tools today to go to one field, to go to Klein-Altendorf, train our data there, and a week later perform the classification task. That actually works with out-of-the-box tools quite well today. But training here and going to a different field or combining systems from different environments is, I think, a big challenge. So if you look into commercial or people who are doing this commercially, they're actually monitoring several hundred farms in parallel, trying to cover all the different conditions that you have, manually labeling all the data, which is a super time-intensive and costly activity. And we think that with the techniques that we use, putting this extra information in there that humans used over quite a while for designing features, and this spatial temporal information and geometric properties, that we can do this with a substantially smaller number of training examples from a substantially smaller number of different farms or different conditions where we need to take that into account. And this is one of the things where I think we have made actually quite some nice contributions. Knowing which pixel is a wheat plant, for example, is often or sometimes not sufficient. Sometimes you exactly want to know the stem location. For example, if you have one of those stamping systems, which basically stems wheat plants back into the ground, or if you use a laser and you actually try to burn the wheat plants but leave the crops there, they actually want to burn the stem of that plant. So you also need to get information where those stems are, for example. You can also do this using those learning-based approaches where on the one hand side you actually learn based on the visual appearance, so you can still label every single pixel in your image what's wheat, maybe even which type of wheat it is, and where you can identify stem location using these learning-based approaches. So in the end you get from one input image multiple output images where you get rather precise stem locations where you can find a stem, But for other weeds, for example, for grass weeds, it doesn't make sense, so that you get actually multiple labels out, and you can actually learn what's the best treatment for those systems. So you can say some of them you should stamp or maybe use a laser to burn them, some of them you should spray, and some of them you should not touch at all. And you can actually use those learning systems and quite efficiently able to separate what you see on the field and which action you should actually execute in order to operate successfully here. And that's some of the activities that have happened in my lab over the last 3 to 4 years, and where we've done quite some nice contributions also in a way that we can now ship them to other partners. So that's something which is more or less ready to use, definitely for research projects, maybe not for a commercial project, but something that you can use in Klein-Altendorf basically to the day if you provide appropriate image data taken from a standard camera. A second question we were looking into here is the question of what you call data associations in the field. So the main question you want to answer here is what I see right now the same area I, for example, have seen in the past. So let's say you have those two images over here, taken at different points in time, and the question is this actually the same place? Are we visually observing the same area? And it turns out, yes, this is the case, but from the visual appearance, it actually looks quite differently. You can actually take an image of the same location over different points in time, and you can see that it actually changes substantially. The question is, are we actually able to relate those images with each other, even if we don't have super precise GPS information? Even if maybe a rough idea which images we may look for correspondencies, but actually finding image correspondencies between this image and this image is actually pretty hard, even for us as a human. So again, these are 4 images taken by UAVs of exactly the same place at different points in time, maybe flying at different altitudes. And for us as a user, making a data association between this one and this one, saying, so this pixel is actually that pixel, is pretty hard. One of the things that doesn't change in the field is to be the location of your crop. I mean, some may die, some may emerge later, but all in all, this is one of the stable patterns you can find. So if you're actually looking into those patterns where the crops are, it starts to become easier. And it turned out what's even easier is looking into the gaps where you expect the plant to be, given the crop rows and given the spatial pattern that the system has recognized, but looking where there are kind of the mistakes are, where the gaps are, and then trying to make data associations or to model a local arrangement of those gaps. You can actually show that they stay constant over time for a much longer period. And you can go back and actually in the design on how you design geometric features, you basically look into neighborhood relations of selecting one and looking how does this relate to some neighborhood relations that you're then able to actually make those data associations over time. So we can fly at different points in time and we can actually make data association, hey, this crop actually is this crop over here. And you can see so whenever those lines are more or less parallel, or if there's a scale kind of going out like a star, it looks pretty good. If you have random connections, it's an indicator that you have done a mistake. So that actually looks pretty good. You could see that the system was flying at different altitudes, but you actually have a rather consistent area that this area over here more or less corresponds to this area over there. And you can do this over time from one week to the next week, from one point in time to the other point in time, so that you can actually then use all the data, build time-aligned 3D point cloud models or 3D point clouds in this case, and then show color-coded, for example, what the different height that the individual plants had at different points in time. If you have all this georeference, you can actually go back to your input image and say, you click on this plant and say, tell me how this plant actually evolved over time. Automatically, you will find which plant or pixel that is in the other images. You can crop that out and then make statistics. For example, looking to the plant, the leaf area or let's say just the green area from the image point of view over different sessions at different sites, and you can actually plot them and see or can analyze the environment based on a single plant in a field and then start making statistics and see how plants have evolved over time. Just using these techniques of being able to interpret what we see, building 3D models, and making data associations over time. And this is one of the activities that we think which will happen in this core project number 1. So these were basically the applications with respect to agriculture that we have done over the last 2 or 3 years, basically 3 or 4 people working on this. And I now want to come in the second part of my talk more a little bit to the techniques which have been developed outside but which are strongly related to those activities that we are doing. And the first thing is the so-called SLAM problem. SLAM stands for simultaneous localization and mapping. That means we want to at the same point in time, localize where we are, so know where we are. And we want to build a map of the environment, so answering the question, what does the environment look like, and localize us in this area. So as the main question that we want to address, what the world looks like and where am I as the robot? So this is a key question that you want to tackle. And that's something I've been working on since 2005 maybe. And if you combine this with exploration, if you start with no knowledge and the system should generate appropriate actions to answer these questions, you are in this kind of combined SLAM exploration problem, which was the key topic of my PhD thesis. So we have built different systems exploring underground environments. So this is a track-based platform equipped with a laser scanner in this example here with an arc of 7 cameras in a certain stereo setup. And driving through the Priscilla catacomb in Rome, exploring these catacombs. And we can collect this data and then actually build 3D models for that. For example, if we take this camera arc over here, we can arrange these camera arc images and make data associations over time and actually build 3D models which look like this just from driving around with this platform. This was a project done together with archaeologists because actually accessing those catacombs is a dangerous thing because they're typically filled with radon gas, at least in Rome and Naples. It's a radioactive gas, which if you breathe it, it gets into a connection with the water in your lung and stays in your lung. So that's nothing you actually want to do over longer periods of time. So the time they spend is actually reduced. It's kind of occasion the upper level of those catacombs, but they typically have 6 or 7 floors. And if you go, because radon is a heavy gas, the further you go down, the more dangerous it gets. And actually, they're typically not able to go down to the lower levels anymore. And you can actually send robots down and doing this kind of reconstruction. We also were able to do this with mounting a terrestrial laser scanner on those platforms. So this is the San Gennaro catacomb in Naples, one of the most famous one. And so this was the first inspection of this catacomb since the 70s. So the second one overall where we were allowed to go in there and actually build 3D models of those catacombs, doing all the analysis in that. And in the end, we were also able to use those systems and put them on your mobile phone, that you can use this cardboard, basically a cheap VR system. You can put it on and actually walk through those catacombs in a VR setup. And we have a small demo in our lab with a slightly more professional setup, basically an Oculus Rift, where you can put on and walk through parts of a catacomb built with these robotic systems or camera laser-based combinations, which requires you to always know where you are and what the world looks like and put this into relation. Some of the things are easy in the catacombs. So for example, everything is static. There are no dynamic objects around like in traffic situations, which make the mapping problem much harder. So it's a kind of simplified setup. Nevertheless, it took quite some efforts to actually solve this in an appropriate way. And again, was a joint effort within a European project, which I have coordinated for nearly 4 years. It finished in the end of 2016 with people from Rome, Leuven, Freiburg, and a lot of different places which contributed to that. We've been continuing on this kind of mapping approaches, also looking into kind of autonomous driving based applications. So this is a data set where you have sensors on a car. There's a Kitty data set, a very famous data set, where you have a car actually driving around. And what we're doing here, from the information that we get from this laser scanner, which are basically local point clouds, we can align them in a kind of a smart or very efficient way, and then building maps of this environment. And whenever the robot comes back to a place where it has been before, you need to make this data association about this is the same place, but it may look different or maybe at a different viewpoint. Then you can form of all this, you can see this through these links here or edges in these graphs as optimization problems, and then solve the overall mapping and localization problem as one of these so-called graph-based optimization techniques. And this is work by Jens Belay, one of the postdocs in my group, who put substantial efforts in building those systems which work robust and provide you with accurate maps of the environment. Again, this becomes tricky if you move to crop fields because everything is very symmetric there. Things may change depending on the current setup, so there are a lot of challenges that need to be addressed. So here this was done with a much more lower quality sensor, actually here on the parking lot behind our building. Actually some people walking around, so you can see the people here always in those laser scans, and trying to actually solve the mapping problems which are involved in this using, let's say, less accurate sensing technologies, and also works quite well here. In this context, what matters is being able to say, have I been at that place before? This is one of the challenging questions. And it becomes specifically challenging if the environment has changed. So what you can see here are two images taken from the same place. Still, this was data set recorded with my car in Freiburg, just having a camera, one in winter, one in summer. And if you see this pair of images within a large collection, are you able to say, am I at the same place as I've been previously, even if the scene looks different right now? So you have two images, and you want to answer the question, have they been taken from the same place? So has the system been at the same position? Although, whatever, one was in summer, one was in winter, and the appearance of those images really look different. This is a problem which happens quite often if you have systems especially operating outdoors. You always see pairs of images here taken from more or less the same place under different conditions. So one in winter, one in summer. This is a data set where a camera was put on a train in Norway and just driving through Norway, recording data all the time. This is in Adelaide in Australia, driving in summer and in day at night. Camera images look very different if you drive during day and during night. These are different setups from data sets that we have recorded, partially others have recorded. And one of the keywords to actually be able to relate those images with each other is not to look into individual images, but to look into sequences of images. Because one image is typically not distinct enough to allow you to make those data associations. But if you look into sequences of images, given that this data hasn't been recorded randomly, I mean, there was a physical camera moving through the environment. So you know, right now I'm at a certain place, I don't know where, but if I take another image 5 seconds later, I may have moved it a little bit, but I'm not randomly at a different place. And if you exploit the sequential information, saying at the two different points in time I was probably going along a similar trajectory, you can relate that with each other. So you can get into sequences of reference images, so images I've taken in the past in my current query sequence, which is the data I record right now, and then you can compare those images with each other with different techniques. So in this example, you can build up basically one of those matrices where bright pixels mean images look similar and dark pixels mean images do not look similar. Just from the absolute value, it's actually pretty hard to identify where that is, but what you can see is a very thin, slightly brighter line in here. It's basically a path through this matrix. And it's hard to see, but if you see it, the whole matrix, it's much easier for you to determine this as a user rather than saying, oh, this is a good match, this is a bad match. So actually what you need to do, you can turn this into a graph data structure and then start searching those data structures. And you can actually find this path through these matrices, which are minimal cost passes, basically. So just by relating how similar images are to cost in a graph, you can solve basically path planning problems, solving this sequential data. The main problem is this is super expensive to compute because you need to compute every image with every other image. This is something which doesn't work in practice. And so people from my group have been looking into the question, how can we actually optimize this? So this was the work done by Olga Wysocka, who's sitting there in the back, on how can we avoid computing these millions of comparisons, but boiling this down to comparisons we can execute in a few milliseconds so that we can actually relate those images with each other. And if you do this, what you get out of that is, what you see here is the current image that you get, and this is an image that you found in your database. And this is basically the part of the matrix which need to be computed. Sometimes you see it's very hard to match those images. You see this no match popping up. Sometimes it's flickering a little bit. So it's not perfect, but you can actually relate those images with each other really well. And for you as a human, it would be actually pretty hard to make those data associations. And just through this sequential information, we are actually able to do that. To simplify it for you a little bit to recognize where you are, we also can do this here, for example, in Bonn. These are data that we have collected. It starts with easy data where we just put a standard GoPro camera, so nothing special, in a car and drove around at different points in time. So you can see this is here Nussallee towards Kaufmannstraße. And here you see how the things evolve. Green means you have done a correct job. Red means you either haven't found a matching image or you did a wrong data association. So both treating this as an error. And you can see you can actually drive around. Again, this doesn't look too dramatically different, but it has been at different points in times under different times of the day against rather similar weather conditions. And this actually works really well. You can make it more challenging, but let's say once we just put a camera on a bike helmet and one in the car, and the points in time being very far apart in terms of time for matching this. And you can see you're shaking with your head a lot, it's much more tricky, and the kind of mistakes kind of accumulate a bit more. Sometimes it turns into this hidden blurs out, which basically means I think I know where I am based on the sequence information, but the images really don't match with each other. Again, you make a larger number of mistakes, but if you take all this information as a sequence into account, it's actually, you still do a good job. And we even got further saying, let's simply download a YouTube video where people have those dashboard cameras there and download Google Street View images and try to match them. So what you see here is Google Street View images from Kiev, and people, it's a random YouTube video, people taking those image data, and you can actually, no, this is not true. This is not this is a camera, a data set that we recorded, so we still knew where we are, but matching this with Google Street View images. But you can also download random YouTube videos, what you will see now here, and trying to match this. Again, the quality is pretty low. We don't have ground truth available for that, of course. But you can still see that you've seen different places, and partially these are construction sites. The scene has changed a lot. And you're still able, through the sequential information, exploit similarities or actually find similar structures. Although, again, appearance looks very, very different under completely uncontrolled environment, knowing nothing about those cameras, downloading stuff just from Google Street View. So you can actually push this pretty far. And so I believe you can actually also use this in the agricultural domain where you have very repetitive self-similar environments to actually improve on this matching and data association problems. Another work we have been looking into change detection, also something which is relevant. This is a work done by Emanuele Palazzolo from my group, which says, given I have a 3D model, which I recorded at some point in time, and I just have a collection of images, can I tell that the environment has changed? So what you see here is the 3D model of the chemistry building without the stadia, and then we have images where the stadia is on, and are we able, without building a 3D model, just based on the image data, say, oops, and the environment has changed over here. So the setup would be you have a 3D model built at some point in time, previous point in time, and you get a sequence of images from your cameras. Are you actually able to say, hey, something has changed over here? And that's a work which requires to know where you are pretty precisely, but once you know where you are, you can actually do that quite well. And basically it works with a trick that you say, I'm getting an image at a certain point in time, and a second image from a different position. Assuming that the 3D model is correct, what I can do is I can take the first image and project it into the 3D model of the world and project it to the viewpoint of the second camera. So what I should observe, given the model is correct, and then compare it to what I actually have observed. And if you do this, for example, this is the image number 1. You project it into the 3D world, and then project it back to a position, a virtual position, where you took a current image. You say, this is what I should see, this is what I actually see, and this is what I should see if the model is correct. You can see the statues at a different point in time, at a different space. Because the 3D geometry doesn't match up with the image. So what you can do is you simply can compare those images with each other, one's where the statue is displaced and one where the statue is where it should be. So the real image and what the world should look like, assuming the model is correct, you can just compare those images and you see inconsistencies. You can see there are ambiguities in there because you do not know which one is correct or which one is wrong or where the change has taken place. So they are kind of two mistakes. And this basically comes from the fact, again, that you have something which obstructs the field of view you don't know about, and then simply objects are projected into a different location in space. And if you combine multiple of those images, you can actually be able to track down where the change has been taken place, and then look into your 3D model saying, hey, something has happened over here. Again, this is something which is relevant if you have a 3D model you build once and you just drive through the environment taking camera data and you want to have a way to say something has changed over here. Next thing is what we often are concerned with is basically scene segmentation. Roughly correlates to the question which parts of my observation actually belong to different physical objects. So you have let's say a 3D laser scan, or I take a picture of the scene and I want to say every person being segmented and say this is a person, or this is an object, this is an object, the chair is an object, the table is an object. And we're looking into that, doing this as fast as possible for online processing. So again, if you're in the autonomous driving domain, we can see the point cloud that we get. And what we want to have is a segmentation which breaks down all the objects in different colors, saying every object is a different color. That's super important if you think about changes or driving applications, moving objects, and you want to deal with those things. And that's the work done together with Igor Bogoslavsky from my group, where we looked into this 3D range data and finding ways for doing this multiple hundred times per second. So there's a single laser scan, and these boxes are kind of all the relevant objects that I find. That's a standard street scene. And this is just done based on the data from a laser scanner. Again, the colors are random right now that could pop up because we don't know what we see. We just see this seems to be an object. You can see this flickering. There's no kind of control over time in terms of tracking. So it's just based on a single laser scan. We can segment this into different objects. But you see, it allows us to actually break down the scene into different objects that we see. And if you track this over time, this actually gets much more stable in terms of this flickering goes away. And we are able, under some assumptions, to actually separate things into different objects or physical objects in the environment. And this could also be relevant if you want to plant different objects you see in the fields or different properties that put up, or you want to separate all the plants that you see into individual objects. And the key thing here is we can do this very fast, 200 times per second, much faster than the scanner can do this, so that we can do online analysis of those systems. This so far is just basically there's something or there's nothing, but we can also enrich this with what we call semantic information. So semantic information basically answers the question similar to the crop wheat example, how to extract meaning out of the raw sensor data. So this pixel is a wheat, this pixel is a crop. What you can see over here is an example, but this is also relevant for other applications like autonomous driving. You want to know this is road, this is sidewalk, this is a car, this is a traffic light, this is a pedestrian. So you want to add this semantic, this meaning to your image data. And again, this is something where deep learning plays a very important role. So you have those networks which basically take the original images and basically reduce it to something which is a lower dimensional representation of this, which can be seen basically as a feature or a compact representation, which allows you to do this classification tasks well, and then upscale this again in order to label your images with what's in there. And these are things that we have not invented, so these techniques are around since, let's say, 7 years or something, or 7 years ago they became very popular. There are a lot of systems which are out there that you can use, but we put a lot of efforts into this, making this as easy as possible to use. So there's a system which is called Bonn, which we published more or less a year, or a bit more than a year ago. And the goal of this thing is make this as easy to use as possible, with the goal of making the semantic segmentation fast. So we want to do that at real time at the frame rate of our camera, not waiting 2 minutes per image, what state-of-the-art approaches partially require. The goal is, again, it's as easy to use. You don't need to code a single line of code if you want to use it out of the box. You can use it as a library or as one of those what we call ROS modules, which is kind of in our own operating system components which interpret our sensor data. But you can also very easily adapt the code and adapt it to your own programs, but you don't have to if you comply with a standard thing. It relies on all the systems which are out there, like TensorFlow is kind of this Google deep learning infrastructure. So we are basically building on top of this and just dramatically simplifying the way you're using those existing data systems or frameworks, which allows you to use all the different GPU accelerators in order to make this learning fast. And this allowed us to actually be compatible with what's out there. So if there's a new version of TensorFlow, a new graphics card, we don't need to care about it because we are just building on this upper level. And the key thing is here, this is something which is ready to use, which you can integrate in your own systems if you need to interpret your data. These are a few examples where we provide already trained models, so you don't need to train anything, you just download this crop wheat classification from data collected here in Klein-Altendorf. You can do this on people semantic segmentation, so you want to label everything which is a person in an image, or for street scenes, for street parsing. And we provide this information, even trained models that you can directly use. And also have kind of a small video that you can see how that actually works in real time live. So it's actually music. I muted the music video. So it's just can download music video, and without any sequential information, label those images. You still see some flickering, and it's not everything perfect. But having this at 70 times per second, being able. So doing this 70 times per second allows you to run this online on a mobile platform, or here for the segmentation of street scenes for autonomous driving. This is kind of, from the performance point of view, slightly worse than what the state-of-the-art does, so 2 or 3% worth. But actually, we are able to provide that at real time, super easy to use. You can just download it and integrate it into your approaches. And that's something where I think we made quite a substantial contribution in here. Last but not least, a few words about navigation. Navigation is the task of how should I navigate, how should I steer my platform to reach a goal location in a near-optimal way. You can think about this as shortest path planning, so something that we all know, or most of us probably know how to do this. That's what the navigation device in our car does for us. The problem which often occurs in real-world situations is that you actually do not know what the optimal thing is. Shortest path is not always optimal. Only if you go somewhere, driving in a field, you have vibrations, you have soil compactions, things you experience while you are there, and what we try to put efforts in, and how can we actually change the whole system in the sense that once we go there, we experience something like vibrations, or we can measure something very locally, which we only get if we are there. We want to adapt our models and improve the navigation capabilities of those platforms that it takes this information into account. A good example from nearby, so this is a way to the Mensa, here this big field, and there are different ways you can navigate. So if the robot is here and wants to go here, it can drive on the pavement. It can actually drive on a straight line, which is the shortest path. This is probably the most vibration-friendly path. Or it can try to find ways which are actually minimizing both of that. And we developed a system or approach which, by going there, the system experiences something, in this case, for example, vibrations, and then can actually relate this to prior data. And this is just basically the aerial images from Google. Just by comparing pixels, what looks similar, once it has driven in this area, it says it's a pretty high likelihood that's actually a good path. And you can actually make predictions over this, and then with a few iterations, with a few trials, find these optimal ways. So if you would have perfect knowledge, the green line is actually your performance. If you just optimize for shortest path, this is your performance. And this is basically the approach that we have developed, that with a few trials, you're actually approaching the optimal solution, something that you never have in reality because you never have full access to what the world looks like, actually quite closely, and in this way come up with optimal or near-optimal navigation strategies, even under uncertainty and even if you don't know all the phenomena which are out there. Which brings me to the end of my talk. What I've tried to do today is explain you what we have done over the last few years, or at least a subset of those techniques. Those where we have a direct application to robots operating in crop fields, but also techniques we have developed which have been, or which stem or have been tested outside that domain, but which probably could impact that and may have an impact on this, and where I see what kind of questions we can answer for you, and also trying to tell you, at least for some of these approaches, this is something you can actually use right now, and other techniques where you say, there's probably still some research work that needs to be done. So that's it from my side. Thank you very much for your attention, and I'm eager to hear your questions. Thank you.
Okay, thank you. Are there any questions? Yes, please.
I have a question regarding your approach where you detected that the statue has been removed.
Yeah.
My question is it also working with crops, because crops are much smaller and also may change the geometry when growing?
Okay, so two questions. They are much smaller. This just depends on the lens you put on your camera, or how many pixels they cover in your scene, and how accurate your 3D model is with respect to your observations. So that's something you could probably scale quite well. The approach is there to detect changes in geometry. So that's the intention of the approach. So if your plant changes, it will detect this change, or is likely to detect this change in geometry. Again, texture also matters. If you have very colors with objects with a unique color, it's very hard to detect actually these inconsistencies. So this would pose definitely challenges to this, but the approach itself doesn't make any assumptions about what kind of geometric change it is. You look for geometric changes. We mainly tested this with objects being there, or we're driving around here on the new campus, and at some point in time they had these Dixie toilets standing around. You can perfectly see when they've been added and removed. We haven't tried it with crops. Actually, if you have trees on your images, and especially if there's wind and the leaves move, that actually is pretty messy, because it says, a lot of things have changed here, although there are not too many changes. So definitely open issues that you need to address in order to apply this into field environments.
Thanks, Cyrill. This was really exciting. I tried out to link
Yep.
a few things. So in crops, if I would, from a sensor, as a sensor person, for orientation, detection, classification in crops, I ideally use not an RGB camera, but slightly more suite of algorithms, of knowledge, of the community which uses RGB.
Mm-hmm.
So your evaluation, if you want to use these predictors for orientation of robots in cropping systems,
Mm-hmm.
how much room is there for new cameras? Should we stick to RGB cameras?
So it's no problem to add additional input representations to those networks. So you can simply add an additional input layer. So this was also the trick that we have used when we used this background knowledge in there. We basically generated new artificial images which resemble those features that users have designed and simply stacked this in this case, as whatever, a 14-dimensional image. So we can do this. The question is, if you go to multispectral data, where you have 200 image dimensions, you may still ask if this is the best way to do, and Ribana, who is more competent on increasing this dimension substantially, would probably argue that that's not the best way you can do. But at least you can add additional input representation into this. You can also combine them. So if you have some background knowledge you want to extract, you have some way for extracting relevant information from this high-dimensional sensor data, you can add this. As soon as you can add this as kind of an image type of representation, this can be easily included. So the only thing that these networks, where they're really good in or optimized for, is that you have a 2D representation like an image with values like a matrix or an image, but you can stack multiple of them into a third dimension if you want to. How many are useful and everything is efficient is you can debate about, but if you have whatever now a camera was having 6 or 8 channels, they can easily add them there. And if these different channels provide you additional information, like for example near infrared is very good for saying, oh, this is vegetation or background, simplifies a lot of your problems. Just added a new input dimension and the problem is much, much easier to use. We had looking into reducing to RGB again a bit because this allows us to use standard cameras. So we don't need to modify a drone, putting a specialized camera on it. If you can buy a drone out of the box for 1,000 euros, we can fly it. We don't need to do any modification. Just take the SD card out, put it in the computer. We have the analysis. That's really attractive for actually getting this shipped out. This was our motivation going back to RGB images. But we still have systems like the wheel platforms where we have this 4-channel camera, which also has the near-infrared information. But again, Ribana is probably the person who is exactly working on this. How can we interpret hyperspectral data with these tools, more from the remote sensing perspective, but she was probably the person who can give you also very competent answers on that.
Yeah, very nice talk, Cyrill. The ability to analyze sequences
Yep.
of images, I mean, this is a really exciting part of the phenotyping that readers can use, because they're stuck currently with statically looking at certain things at different points in time.
Yeah.
If they could actually make use of sequences of images. But the thing is, I think that they would be interested in the differences in the sequences rather than the similarities over time, to get an overall, like the way you described, am I in the same place?
Yeah.
And so just thinking forward, something for discussion would be just how sensitive is the finding the difference in sequences between two genotypes or two treatments, and the change detection rather than the similarity detection.
Okay.
But yeah.
So we use the similarities, finding those similarities in order to fix the position that we know it's the same place. If you have more control about your environment and you say, I'm fixing the position or this external variable, then it's much easier to analyze your sequence and then spot the differences. So it's depending on which parameter you fix and which parameter you keep variable. If you say we only are interested in change, the best thing I can do, I can turn around and observe the white wall instead of you and say, oh, perfectly, super different. If I constrain myself looking at you, and I have a sequence of today and a sequence of tomorrow where you're wearing a different pullover, I can perfectly spot that. So it's kind of this relation of which variable you fix and which variable you keep free, and then we just in the end get a comparison measure. We get a value between whatever, 0 and 1 or 0 and infinity, which tells you similar or different, and we can just optimize for increasing this number or reducing this number, so this doesn't make a difference then, once this external constraint about where I'm looking to is fixed. So that should be doable.
But probably you can have you fix the position as the orientation.
Yeah, I know, but it's always the question of kind of, I totally agree with this. This was explicitly done as an orthogonal methodology where you want to be single sensor. But of course, if you have this information, you can do much better.
Okay.
What?
I had also two questions. One is almost answered. Recognizing the place where I am should be quite easy with the knowledge that you have in your group, right?
Of course. I mean, we also, it's not that we completely ignore GPS information. The question is kind of how far can you go, because there are setups where your GPS information is not super reliable. You can see this as an alternative methodology. You say, of course, if you have 4 sensors which can localize you, use all 4 of them, have redundancy in there. But if you then drive to a parking garage, it will be a pretty hard job for Heiner to tell me, based on the GPS, where he is. We can still use the camera information. Only using cameras, being outdoor in a good GPS condition, of course, Heiner can do a better job. So it's the interplay of different methodology or different sending modalities and how to combine them in an appropriate way that we have high precision in terms of we know precisely where we are and having the robustness that we actually need to work under, I don't want to say all conditions, but maximize the number of conditions we can actually work in.
And the second question, if I'm allowed to.
Of course.
I like very much that you try to link your presentation to the core projects. So my question would be core project 4.
Yep.
You showed already very impressively how you can detect and also remove weeds. And I think we should build on that.
Oh, that's the idea, to build on top of this.
Knowledge that you have already. What do you think? What could be the next step? What could be a challenging task or question, but that is, let's say, that we can manage to solve within 2 or 3 years?
Okay, so you have to distinguish several things in here. One thing is kind of how perfectly is this working, under which conditions, and which part is working perfectly. For example, if you see this laser-based treatment, this was done in a very controlled lab environment where the light form was not moving. This is something which doesn't work right now on the field out there. The stamping system that you've seen, this was done in this Flourish project, European project. The stamping system was actually developed by Bosch. But the problem is, if you have the stamping system, you actually can't drive too fast. So this was limited to something like 30 centimeters per second, which is clearly too slow to operate on the field. We also had a selective spraying system in there, which then was easier. So you basically spray only the plants that you want to spray and leave out the others for spraying. This is much easier to realize. This is probably the thing you would start with. Again, generalization, we have done quite some steps in the last year, I would say, to improve this generalization capabilities. Integrating very different types of weeds which all need different treatment, and not having this only for sugar beets. So we are mainly working with sugar beets, although we have trained it on different systems, but having kind of one classification system which does all, there's still a way to go. But for building a first prototype, a demonstrator that you can actually put out to the field and show what you're doing, we have actually the perception tools quite in a good shape, so that we actually could ship at least the perception stuff, I don't want to say immediately, but with some engineering integrating effort, but from the research point of view, for the weeding application, we can do a good demonstrator. It becomes much more difficult if we think about plant protection, if we think about nutrition. These are things which are much more difficult, at least from my, not only from my perspective, this was a result of the discussions that we have had, but where the techniques won't scale in the same way as I do for the weeding application. At least that's the feeling that I have right now. So for building up a prototype, a demonstrator, we have the perception tools in hand that we could start with that quite quickly and integrate it into the system. But yeah, there are still a couple of open issues. How fast can you go? How quickly can you apply the things so that it becomes actually reasonable or also commercially viable at some point to doing this? If you can only go with 20 centimeters per second over your field, it's probably not scaling very well or being not that attractive. There are a lot of things in terms of coordination of actuation and perception. There are a couple of open issues we still need to address, but a demonstrator, I'm confident that we can ship something. Yes, please.
Yeah, one question related to the Bonn net.
Yeah.
Is the model architecture and image training data optimized for the application with plants?
No, it's not optimized for this. So it's actually tried to make it as simple as possible. So you even can just copy your positive and negative examples into different directories, and then just run it, just go through the directory structure, infers the labels based on directory names. So you can do this really without any coding. So there's no special optimization for that domain, Bonnet itself right now works mainly on RGB images. I'm not sure if the current version which is out there can have images which have more input dimensions. We have an internal version, but I'm not sure if this is already the one which is shipped out there. But there's currently no optimization for the application at hand in terms of the image data that you actually need. So it's standard RGB images.
Okay, if there are no further questions, then thanks again.
Thank you very much for your attention. And again, the next PhenoRob seminar series will take place on Friday, 11th of January, and then in Jülich. So we have this idea of changing always between Jülich and Bonn. But we plan to provide a shuttle service with the bus going to Jülich. You need to register before that so that also the entrance into Jülich and all the security checks will be simplified. So we will send an email around, so register if you want to go to Jülich on the bus. Going with us is easier than going on your own, let's say it that way. Thank you.
And, just to put forward, in the next year we will have a regular seminar series.
Yep.
Once per month. Usual on Friday.
Every second Friday of the month.
Every second Friday of the month. So, take it in your calendar, and alternatively, starting with Jülich and then Bonn, then Jülich.